Okay, good afternoon and welcome to my presentation. The title is Small Signal and Transient Stability Investigation of Inverter Grid Synchronization. My name is Alexander Schöley and I'm from the University of Rostock. At first, I'll give you a quick overview of what can you expect in the next minutes. In the beginning, I will give a short introduction, then I will describe the system and actually state the problem. And after that, the main part is the stability investigation, and the findings will be verified in some simulation results. And the presentation closes with a summary. Well, the main topic is the grid connection of power generators to the energy grid. And I'm sure you're aware of the main trend that is happening, which consists of the decrease of conventional power generation and an increase of the so-called renewable power generations. And unfortunately, those new renewable power generators have significantly different properties than the known conventional one. And this is mainly due to the grid connection because of their electronic devices called inverters. And there's a standard control technology to control those inverters and feed the energy to the grid. That's called voltage-oriented control. But the voltage-oriented control need a proper grid synchronization to work. And it is also known that the grid synchronization fails in weak grid scenarios. But although this is it's a known problem, it's quite hard to pinpoint down the exact circumstances when it's successful and when it's failed, which of course raises the motivation to perform a stability analysis of the grid synchronization problem. Let me introduce the system here. This is a basic functional block diagram of a inverter-based grid connection with the example of the wind turbine system. Basically, the grid connection consists of a back-to-back converter, which is comprised of a machine-side converter and a grid-side converter with a DC link in between. And at the output of the grid-side converter, there's a hardware filter to smooth out the output signal. And this system is then connected to the energy grid, here represented by an impedance and the idle grid. What happens is that the machine-side inverter rectifies the electrical signals from the turbine's generator and the electrical energy stored in the DC link. And then the grid-side inverter has to create a three-phase AC voltage that matches the grid voltage in terms of frequency, in terms of amplitude and phase angle. But frequency is the most important one. So the grid-side inverter needs some information of the grid voltage, and this is usually detected from this measuring point. And a standard sensor to do this is a PLL, a phase locked loop. And when the fundamental grid frequency is successfully detected from this measurement voltage, we say that the grid synchronization was successful. Now, to dive a bit deeper into this system, let's look at the grid-side subsystem, which is highlighted in green here. And on the next slide, there's a circuit diagram that is the basis of the model equations we use. Here, the grid-side inverter is reduced to an idle grid-side inverter, which is just a voltage source that outputs a sinusoid voltage with a tunable amplitude and phase lead of this form. And the amplitude and this phase lead is highlighted here because we consider this as control inputs. This inverter voltage is then connected to the grid voltage on the right side by an impedance network. And the capacitor voltage highlighted in yellow is the measurement voltage, and the three-phase equivalent of that is used as an input to the phase lock loop. I have to explain the phase lock loop a little bit more in detail. So here's a bar lock diagram of that, and the main part is the input transformation, which transforms this three-phase input voltage to the signal UQ. And the basic functionality is that when UQ is 0, the phase of the PLL, so this phi PLL, exactly matches the phase of the input voltage. So this is the first part that is shown here. So UQ is null, the phase equals exactly, which shows the steady state of the PLL. And when this is not the case, the PLL will adjust a little bit the internal frequency here, omega PLL, so that phi PLL gets accelerated or decelerated accordingly. Okay, back to the circuit diagram. You can imagine that by measuring this voltage at the capacitor, it might not be possible to detect exactly the properties of the grid voltage. And this is because there's an impedance in between with a voltage drop. And when this voltage drop cannot be neglected anymore, this whole scenario is considered a weak grid scenario. And actually, we can go a little bit deeper and can conclude that the measurement voltage is a superposition of the inverter voltage and the grid voltage. So one part of this measurement voltage depends on the inverter voltage and one part on the grid voltage. This, of course, has a consequence for the PLL, because when we apply the input transformation to this superposed voltage, we find that the signal UQ is also composed of two parts with the same structure. So there's one part inverter voltage and one part grid voltage. And I have written them down here. Please just note that the part that depends on the inverter voltage is a constant for fixed input values, and part of the grid voltage is a sinusoid because it depends on the state phi PLL. Okay, now we can perform or conduct some stability analysis at first for the small signal case. So small signal case means we are only concerning with specific equilibrium points or operating points. We first have to calculate them, and there we find that there are actually two possible solutions. And so we conducted a linearization in those two operating points and calculated the eigenvalues. And they are shown here in this graph. You can see that for solution 1 in blue, the eigenvalues are all in the left half plane, so that means the system is stable. But for solution 2, there are one of the former complex conjugate eigenvalues are now real eigenvalues, and one of them is shifted to the right plane. So that means that the solution 2 here is an unstable system. And we can a little bit more go into detail with that with the two parts of the signal UQ. They are plotted here. And at first, this blue part, it's a sinusoid part that depends on the grid voltage, and the constant part in red, that's the part that depends on the inverter voltage. We know that the equilibrium or the operating points are at the intersections, and you can see there are two. Yeah, we can now perform a qualitative investigation of those 2 points. Let's consider first this first point on the right-hand side, marked with delta 1. This delta 1. Remind that this plot is drawn with dependence on delta, which is just a shifted version of phi PLL. And when you now consider a small disturbance of delta to bigger delta values, you can see that the system reacts with a UQ that is less than 0, which means that phi PLL and delta moves back to the operating point. And the same thing happens when there's a small disturbance to smaller delta values. So you can consider this first solution as a stable operating point. When you do the same qualitative analysis in the second operating point, you find the exact opposite circumstances. So when the system is a little bit disturbed, it will react with a further acceleration of the phase angle, and it will move out of the operating point. So for the small signal case, we can conclude that the second solution with delta of the operating point greater than 90 degrees is definitely unstable. However, we cannot really conclude that the delta with that is characterized by less than 90 degree is stable, because it's just a necessary condition, and sufficient condition has to be checked by performing, for example, the eigenvalue analysis. But this yeah, gives some more insights to look at the transient case, which we've done here. So now this is the same diagram, but now we are considering a step of the operating points. So at first, we are at this operating point 1, and then all the control input YL values step up, so that the operating point, the target operating point, is this yellow one here. But initially, the system is in the state delta equal delta operating point 1. And now we can look at some intervals. In the first part, we see that UQ is greater than 0. That's why phi and delta accelerates, which is intended behavior. So delta moves up this curve until this point. And when delta overshoots, it will enter this second part where UQ is less than 0. So delta will deaccelerate. And it might decrease eventually when it doesn't touch the part after this second solution of the second operating point. Because when that happens, we enter a critical region, which means that the UQ value is again greater than 0. And so the circumstances are that the variable delta in VPLL accelerates further, so that the operating point 2 cannot be reached anymore. Which means that this delta critical is actually the maximum permissible overshoot for the state variable. This is here pointed out on the next slide. So the stability condition for the transient case is delta has to be smaller than delta critical, and it can be translated into values of VPLL. And I performed some numerical simulations to show you what happens. We are in this plot. This is just one. It's always a step up of the operating point, starting with VPLL at 0. And the dashed black line marks the target operating point, and the colored dotted line marks the critical value. For this first simulation, you see that the overshoot is considerably below this critical value, which means that the target operating point is reached. In the second experiment, this was designed so that the critical value is also not reached, but just barely. So you can see there are considerable oscillations, but eventually the operating point is reached. In the third operating point, the state VPLL hits the critical value, and you can see that after this point, the plot diverges. So the target operating point cannot be reached anymore. But I'm sure you know that there's a strong connections between damping and overshoot. So we can also retune the whole system to have more damping. This can be done by reparameterizing the PLL. And this is done in the fourth simulation. Here we used a damping of infinity, which means no overshoot at all. This is just an extreme example, which comes with, of course, another which comes with more difficulties, but just to show you that by retuning the PLL, we can decrease the overshoot. In this case, decrease the overshoot to 0, which means that we will not hit the critical value, and we can reach the stable operating point 2. Yeah, to summarize up, this contribution was about the PLL-based grid synchronization and considers weak grid scenarios. And a control engineering analysis was performed for the small signal and the transient case. And some stability conditions were derived for those cases. And the simulation, the findings were validated in numerical simulations. Some few words for future work. This transient stability condition is not really satisfying because you have to perform a simulation to know what happens. So it would be really useful to have a criterion that shows whether this condition is met without performing simulation tests. And also, this whole analysis was done without considering power electronic effects, so they should be introduced afterwards. For example, what about the current amplitudes and what about non-idle behavior of the inverter when the switching patterns are considered. So this concludes my presentation, and I'm thanking you for your attention.